So the first section is about how to charge a capacitor. So charging a capacitor, we have seen this before. We need just to connect a capacitor to a battery. Okay, so we take an initially uncharged capacitor, so the uncharged capacitor, of course, it has at t equals 0, so initially at t equals 0. Second, what we have, the charge is 0. That's what means uncharged capacitor. What is the voltage across the capacitor? Let's call it delta Vc. If the charge is 0, the voltage is 0. So here we have a problem if we connect a capacitor directly to a battery without a resistor. So at t equals 0, we have the difference in potential across this device, which is capacitor, is 0. And the difference in potential across the battery is E, the EMF. So if we connect them in series like that, it will not work. So we need another device, which is a resistor. The resistor here, it will control the difference in potential between the battery and the capacitor. Initially, by the way, if the difference in potential is 0, what do you think the current? The current is going in this direction. What is the current in the circuit? Well, if the voltage here is 0, so we have the voltage cross the EMF is equal to the voltage cross the resistor. So we will have, from that, we will deduce that the current, the initial current, is E over R. Okay, that's just our prediction. If we wait longer, so after long time. What do we mean by long? So mathematically, t equal infinity. So what will happen at t equal infinity? Well, the capacitor is fully charged. When the capacitor will be fully charged, when the potential across the capacitor is equal to the EMF. So we have delta Vc is equal to E. What will be the charge then? If the voltage here is E, the charge is just the capacitance times difference in potential. And the current, the infinite current, is 0. Why is that? Because the battery is charging the capacitor. So here we'll have a positive charge appearing in this plate, a negative charge appearing in this plate. When the capacitor is fully charged, well, there is no flow of electrons, so there is no flow of current. So that's what we predict. Now, if we draw a schematic of variation of charge, we will get something like this. This is time. This is a charge Q. So what we will have, the charge going from 0, going up like that, and infinity it will reach the asymptotic value. The asymptotic value is just Q infinity, which is C times E. The voltage, well, it will have the same shape. It's also increasing, the voltage cross capacitor. So it's also increasing in same fashion. Start from 0, and it goes to the asymptotic value. What is the asymptotic value? It's just the EMF, E. What about the current? Well, the current, we see that it starts from a certain value, E over R, and it decreases until reaching 0 at infinity, so it will decrease exponentially, actually. So this is E over R, and it decreases exponentially in this fashion. So that's what we expect from this problem. So the question now, well, what is this equation? What is the real equation of charge, of voltage, and of current versus time? So to do that, we will just simply apply loop rule. Loop rule to our circuit. So loop rule just to remind you, the sum, algebraic sum of difference in potential across different components on a closed path is equal to 0. So that's closed path that I choose. Okay, clockwise direction. So let's go and read difference in potential. So we have E, the EMF, minus Ri, and in this direction, what is the potential? If you look at it here carefully at this capacitor, we have a positive plate here. This plate is positively charged, plus Q. This plate is negatively charged, minus Q. So what happened to the potential? Increasing or decreasing? Of course, decreasing. Okay? The positive plate will have a higher potential. The negative plate will have a lower potential. So the potential is decreasing, so it means we need a minus sign, delta Vc. So here we have E minus R. What is the current? The current is dq over dt. So I will use just that, dq over dt. And what is the difference in potential across capacitor? So that the charge over C equal 0. What we have here, we have an ordinary differential equation of order 1 on a charge. By solving this equation, you will get, so we need calculus. So calculus will tell us that this is equal to, solution of this equation is CE 1 minus exponential minus t over RC. That we usually write CE, that's just Q infinity, that's the infinite charge. If we wait infinite time, the charge on capacitor, it will have this charge, Q infinity. 1 minus exponential minus t over tau. Tau is capacitive time constant tau is equal to RC. So this is homogeneous to time. If you want to convince yourself, we can do a unit analysis. So what is the unit of resistor? That's ohm. Unit of capacitor, that's farad. But ohm, that's just ampere over, volt over ampere. And farad is just coulomb over volt. So you will get coulomb per ampere, which is not more than second. Charge over current, just time. Okay, so indeed is a time constant. When the time t equal tau, so I replace here t with tau, what I get? The charge equal to Q infinity 1 minus exponential of minus 1. If you calculate this using your calculator, you will get 0.63 Q infinity. What this is mean, when t equal tau equal 1 time constant, the capacitor is charged up to 63%. So, difference in potential cross capacitor, that's quite easy. Potential cross capacitor, that's just charge over C. So from this equation, we can deduce that this is E, the EMF, 1 minus exponential minus t over tau. That's the variation, the time-dependent variation of the voltage across the capacitor. What about the current? Well, the current, that's just dq over dt by definition. So all what you need to do is to derive this equation. If you do that, you will obtain E over R, that's the initial current, exponential minus t over tau. Okay. So here we are done with charging. Let's go to the next topic, which is discharging of a capacitor. So here we will discharge a capacitor. So discharging capacitor, it means I connect the switch to the point B here. So I start with an initially charged capacitor. So the capacitor initially has a charge Q naught. And we connect it just to a resistor in series. So we have RC series circuit. When I wait longer time, the charge will be 0. It will discharge capacitor. So how this happen? We want to write differential equation that show that. So where is direction of the current? The direction of current, so we have positive charge here, so direction of current will be like that. Now we need just to take loop rule, this one, and we draw a loop, and we write a loop rule. Loop rule. So here the potential is increasing. I go from minus potential to positive potential, so I'm increasing from lower potential to higher potential. So I'm increasing potential, so we have plus delta Vc. The loop direction is direction of current, so we have minus Ri equals 0, Q over C minus Ri equals 0. And we want to solve this equation, but we need to write I as function of Q. Well, like we did before, I equal dq over dt. But not exactly. Why is that? The charge is decreasing. We have a decreasing charge. When the charge decreases, dq over dt is negative. But the current, we know that the current is positive. So in order to have a positive current, we need a minus sign here. So our differential equation, that's very important. So our differential equation, it will be Q over C minus Ri, well, that's plus R dq over dt. That's the differential equation, equals 0. When we solve this differential equation, we get Qt equal Q naught, the initial charge, exponential minus T over tau. What is tau? Same time constant, R times C. With tau equal R C, same time constant. So we have the same time constant for charging and discharging. Voltage cross capacitor, well, that's just Q over C. So you have Q naught over C exponential minus T over tau. So the charge is decreasing, the voltage is decreasing. What about the current? Well, the current, we have just the formula here, minus dq over dt. Otherwise, you will have a negative current. Let's give you Q naught over RC exponential minus T over tau. So the current also is decreasing. Everything is decreasing when we discharge a capacitor. So I will stop here and see you in the next video. Thank you for watching.